Hello everyone and welcome to this week's lecture. So for our final week, we'll be looking at some guidelines as far as ethics and safety of AI, which is chapter 27 in your book. So the outline of this lecture, we will start with a discussion of the limits of AI and then try to answer this question, can machines really think? And then finally, we will discuss the different aspects of ethics in AI, from bias to other issues that can arise as we develop models. So, philosophers have been asking big questions for a long time. For example, how do minds work? Is it possible for machines to act intelligently the way people do? Are these machines one day will have real conscious minds similar to humans? Some additional questions we can ask as well are what are the ethical implications of intelligent machines in day-to-day use? Should machines be allowed to decide to kill humans, for example, in drones? Can algorithms be fair and unbiased? What will humans do if machines can do all kinds of work? What will then be left for us to do, essentially? And how do we control machines that may become more intelligent than us? So these are all important questions. We're going to try to address some of them today. So let's start by discussing the limits of AI. So in 1980, the idea that machines could act as if they were intelligent was new, and scientists decided to make a distinction between what they called weak AI and strong AI. So weak AI would mean that it essentially assuming that machines could act as if they were intelligent. However, strong AI would be an assumption that machines do so are actually consciously thinking, not just simulating thinking. Over time, the definition of strong AI shifted to refer to what is also called human-level AI, or you hear that frequently these days, general AI or Gen AI, which are programs that can solve an arbitrarily wide variety of tasks, including a new one, and do that essentially at the human level. So critics of weak AI, who objected to the very possibility of intelligent behavior in machines, now appear short-sighted, essentially, because essentially the rapid progress of recent years proves that there's almost no limit to what AI can achieve. Okay, so let's look closely at Turing's argument. Essentially, Alan Turing was the first person to define AI, and he was also the first to raise possible objections to AI, foreseeing almost all the ones that raised by others after him. So Turing's argument from informality of behavior says that human behavior is far too complex to be captured by any formal set of rules. Humans must be using some informal guidelines that could never be captured in a formal set of rules. And so he concluded that a computer program will never be able to simulate a human, essentially. Now, this view had many proponents. And however, as we saw throughout this course, agents from the simplest one that we discussed, chapter 7, are still able to solve a lot of problems using probabilistic reasoning. So even if there's no fixed set of rules, they can still use probability And these probabilistic reasoning systems are more appropriate for open-ended questions. And we also show in chapter 21 that deep learning systems can do well on a variety of informal tasks. Again, because over each training iteration, they learn better to simulate a human, essentially. So we can conclude that the critique is not addressed against computers, but rather against one particular style of programming, which is logical rules. So if we avoid using a fixed set of rules and instead use probabilistic approaches like we've been doing, then maybe Turing limitation does not apply anymore, because it's not just going to be a rigid set of logical rules. For example, one of the arguments that were presented says, for example, consider an agent whose understanding of dog comes only from the word dog, comes only from a limited set of logical sentences, such as it is at a disadvantage compared to an agent that had actually watched dogs or played fetch with them or has been licked by a dog. Okay, so just understanding what is a dog does not mean you really know what a dog is. So the embodied cognition approach claims that it makes no sense to consider the brain separately. So cognition takes place within a body which is embedded in an environment. So we need to study essentially the system as a whole, not just the brain by itself. The brain's functioning exploits regularities in its environment, including the rest of the body. Now, if we look at another approach, which is essentially called the embodied cognition approach. So that's essentially what we just summarized, which is cognition takes place within a body, which is embedded in an environment. Another argument is the argument of disability. The argument from disability makes the claim that a machine can never do a task X. Okay. For example, Turing lists the following: some of the tasks that a machine can never do: be kind, resourceful, beautiful, friendly, have initiative, have a sense of humor, tell right from wrong, make mistakes, and so on. So we can see that some of these tasks are easy. We're all familiar with computers that make mistakes. Okay, so saying that really computers cannot make mistakes because they're not human doesn't make sense. Another example is computer chess expert predicted, for example, that people by 2050 will fall in love with humanoid robots. As for a robot falling in love, that's a common theme in fiction. Computers have done things that are really new, making significant discoveries in astronomy, mathematics, chemistry, computer science, and other fields. Overall, programs exceed human performance in some tasks, while lagging behind on others. The one thing that is clear is that they can do is be exactly human. So even though they approach human performance on many tasks, they cannot be exactly human, essentially. So Alan Turing, in a famous paper from the 1950s, suggested that instead of asking whether machines can think, we should ask whether machines can pass a behavioral test. which this test essentially is still known until today. It's called the Turing test. The test requires a program to have a conversation using typed messages with an interrogator for 5 minutes. The interrogator then has to guess if the conversation is with a program or a person. If the program passes the test and is able to fool the interrogator 30% of the time, then in that case we would say that this specific AI model passed the Turing test. So for Turing, the key point was not the exact details of the test, but instead the idea of measuring intelligence by performance on some kind of open-ended behavioral task, rather than just some philosophical discussions. So Turing declares that by the year 2000, if we have a computer with enough storage or enough memory, it should be able to pass his test. However, in 2025 now, there's no agreement on whether or not the program was actually able to pass the Turing test. In 2014, a chatbot was able to fool 33% of judges in the Turing test. The program claimed to be a boy from Ukraine with limited command of English, and this is how they explained its grammatical error to the interrogators, essentially. But again, these judges were amateur judges, but no professional, well-trained judge has been fooled yet. There are actually some Turing test competitions that take place every now and then, and they actually led to better chatbots for applications like customer support and so on. But really, the AI community was not focused on developing an agent that will beat the Turing test. Instead, AI researchers focused more on developing agents capable of playing chess or Go or some video game like StarCraft 2, or even taking an 8th grade science exam, or identifying objects in an image like we saw with computer vision last week. In many of these competitions or tasks, programs have reached and even exceeded human level performance. But again, that doesn't mean the programs are human-like outside of that specific task. So a program that's trained to play Go is not considered human-like at other tasks other than playing Go, for example. But the idea is to improve basic science and technology and to provide useful tools, okay, that will contribute to pushing the field forward, essentially. Okay, so let's next discuss the question of, can machines really think? Let's do that in the next part of this lecture.